Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 25, and we're introducing the Poisson distribution. Last time we discussed the negative binomial distribution and actually did some examples. We talked about its moment generating function, its mean and variance. Remember that the negative binomial is where we repeat trials, which are Bernoulli trials, until we obtain the rth success or whatever is occurrence that we're trying to study. And so R can be 1, 2, etc. And remember that this is a generalization of the geometric distribution. The geometric distribution is when R is equal to 1. So it's always the first occurrence. All right. So let's talk about this section, 2.7, the approximate Poisson process. We're going to define that, which will lead us to the Poisson distribution. Its moment generating function will be derived. Then we'll derive its mean and variance and discuss some shapes based on various lambda, which are the parameters for this distribution. And next time we'll do some examples of the Poisson with the Poisson distribution, and we will talk about the approximation for the binomial using the Poisson and an example of that. So let's get started. We're going to start with that definition of the Poisson process, and actually we call it the approximate Poisson process. So let the number of occurrences, and that's what we're interested in, we're going to count the number of occurrences for the Poisson. In a given continuous interval, later we'll talk about the exponential distribution if we're talking about the interval. But notice it's a continuous interval, but we're doing the counts. So we're counting the number of occurrences in a given continuous interval. We have an approximate Poisson process with a parameter lambda greater than 0 if we meet all three of the following conditions, and that is that the number of occurrences in non-overlapping intervals are independent. The probability of exactly one occurrence in a sufficiently short subinterval, let's call it length h, is approximately lambda h. So notice we're using that word approximately a lot. And then the probability of two or more occurrences in that sufficiently short interval, subinterval, is basically 0. So again, essentially 0 or close to 0. Okay, very close to 0. So that brings me to the remark that we're using approximate for the Poisson process because we use approximately in number 2 and essentially in number 3 up here, as I pointed out. And we're able to avoid a very technical definition which uses something called little o notation. And so that would mean that we'd have to introduce not only that notation, but an alternate notation, big O notation, talk about the differences of those and try to get you familiar with that, and then come to this fairly technical definition. So we're going to avoid that and use this definition, which is a very good introductory definition for someone who's just learning about the Poisson process. And just notice that we frequently will drop the word approximate, but we're still referring to this approximate non-technical definition. Okay, so there's a derivation for the PMF, logical derivation, talking about the different ways that this is comes about, the probabilities and such. You're welcome to look at that in the book. I'm just going to go ahead and give you the PMF. Notice that if I don't have a value of lambda, not only do I have to have the support of x, I also have to tell you the values that lambda, the parameter, can take. So when you're giving the Poisson distribution, the PMF, you need to give all of this. Now, if once you plug in for lambda, you don't need this anymore because that value is going to be greater than 0. Once you have lambda, you don't need to tell me what lambda can be. We've already defined a lambda, so we're really just worried about what we don't know, which would be x at that point, or what x could be. And x is the number of occurrences, you could call it successes, and lambda is the average number of occurrences or successes per that defined interval. Okay? This is a defined or set interval. The Poisson random variable is most commonly used to model the number of random occurrences for some event, some random process in a, again, specified or set interval or unit of time or space. So this interval can be time, it can be space, and let's talk about some examples of that. We could count the number of cell phone calls passing through a tower between 9 and 10 a.m. Here's time. We could talk about the number of flaws in 100-foot increments of wire, that's space. In fact, it's length. And then we could talk about the number of customers arriving at a ticket window between noon and 2 p.m., that's time again. And number of defects in 100-foot rolls of aluminum screen that is 2 feet wide, that's area for our interval, so space. So these are some different examples. Again, we're focusing on the counting, the number of cell phone calls. So the number of cell phone calls, and we're talking about the number of flaws, and the number of customers, and the number of defects. So we're focused on these in this section, and in the exponential section we'll focus on the interval. Okay. So to understand, again, you can look at the PMF derivation on page 82 of the textbook. So let's verify that this is in fact a PMF. It's pretty easy to see if you look at the PMF that, where did it go? Here it is, that lambda has to be positive, e is always positive, raised to any power, and we're saying x is between 0 and infinity, positive, and so 0 factorial is 1, so this f of x is always positive. So that's an easy part. So we're going to use our knowledge from calculus of the Maclaurin series of e of x, e to the x. And so the sum of the kth derivative at 0 of x minus that same value, which is 0, raised to the k factorial, that's called a Maclaurin series. And if we work this out for e to the x, then we end up with this expression. This is the limit of this, or the limit of, if we had n up here instead of infinity, as n goes to infinity, then that would be e to the x. So this is one of the definitions of e to the x. There's quite a few, actually. So when we look at the summation here, to see, so this is the sum of f of x equals 0 to infinity, so that's the sum of the PMF. We plug in, and then we can pull e to the negative lambda out because it doesn't have an x in it. So everything else has to stay, and that's the sum of lambda to the x over x factorial, and that is a form of this, so that is e to the negative lambda times e to the lambda, so we have 1, so it is in fact a PMF. Now let's look at the moment generating function. So expected value of e to the tx is the sum of e to the tx times f of x. And again, we pull the e to the negative lambda out, and then we look at this. We want this raised to the x because this is, and we want to put them together, and then we end up with lambda e to the x, e to the t, raised to the x power over x factorial, and this turns out to be e raised to the lambda e to the t. And so we have, combining the exponents, e raised to the lambda e to the t minus 1. If we take the derivative of this, then remember we're taking the derivative with respect to t. So we're taking the derivative of this, and we look, and so we take e to the t times the derivative of what it's e to the lambda e to the x, this exponent. And so what we do is we take this e and then times, using the chain rule, the derivative of the exponent. And so we end up with lambda e to the t times e to the lambda quantity e to the t minus 1. Hard to say, easier to see, right? Let's take the second derivative. So we take the derivative of the first derivative. So what we do is we take the first times the derivative of the second, and so we end up with this expression, lambda e to the t quantity squared. And then we take the second times the derivative of the first, and there's no reason to really simplify this because we're going to plug in t equals 0 when we evaluate the moments. So mu is equal to e of x, and that is m prime of 0, and so we substitute it in, and I'll let you look through that on your own and see that we get lambda. So mu is equal to lambda. Now, don't forget that sigma squared is not equal to ex squared. This is, when this is at t equals 0, this expression is e of x squared. So e of x squared minus e of x quantity squared, which I've written out as m double prime of 0 minus mu primed, and then we plug in zeros for everything. And by the way, we already know that mu is lambda, so I've plugged that in. Then we end up with lambda squared plus lambda, that's e of x squared, by the way. And then this is minus mu squared. Notice that the lambda squares cancel, and we get lambda again. So this is a very easy distribution to remember the mean and the variance. Because they're the same, they're lambda. There is an alternate proof in the for the definition of the using the definition of the expectation in the textbook. And they use e of x and then e of x to x minus 1. Well, it looks like my shapes didn't show up in this video, so we'll use them we'll wait and present them in the next video. Don't forget to scan your lecture notes and upload them before midnight of the date listed on the course calendar. In this case, I think what you need to update is your list of distributions. And if you have questions, come to virtual office hours. If you can't come to virtual office hours, email me, but make sure you email me a picture of the work, your work, and the problem. And if you do that, then I should be able to help you even if I don't have access to the problems or solutions. We will see you next time, and take care.